Good evening, Stratford. A pleasure to be back to talk to you once again. This time, dealing with the rather trivial subject of how the universe began. As you can see, a brief description of the origin and the very early history of the universe. And let's see how long it takes to get through this. Well, it'll take me longer to describe than it actually took to make the universe in the first place. If we have a look at the universe in which we live, this might look like just a bit of CGI, but treat this more like a 3D atlas. We've looked out into the universe, we've mapped the positions of galaxies, and we've measured the distances to galaxies. Therefore, we've been able to make a 3D map. And this, if you like, is a fly-through of a 3D model of our universe. So we notice, well, of course, we notice it's full of galaxies. But also we notice that the galaxies aren't uniformly distributed throughout the universe. Some areas seem to be relatively sparsely populated, and every once in a while we seem to fly through a region which has huge numbers of galaxies. And sometimes these galaxies seem to line up in lines or filaments. And it's clear that there is some sort of large-scale structure to the universe. But the bottom line is, we know that there are huge numbers of galaxies out there. This fly-through is really only dealing with some of our local galaxies, clusters and superclusters of galaxies. But when we look at something like the Hubble Deep Field, it's looking at a tiny patch of sky with very long exposures, looking long way back in time. And because we can see thousands of galaxies in a tiny patch of sky, and we think this is the same in all directions we look. They checked in different directions just to make sure that was correct. If we see thousands of galaxies in a tiny patch of sky, we can calculate roughly how many galaxies there are in the observable universe. And it turns out to be many hundreds of billions, perhaps even as many as a few trillion galaxies. Each of those galaxies contains hundreds of billions of stars and a whole shed load of gas and dust and other things. So the real question is, where did all this stuff that we see in the universe come from? So what am I talking about? I'm talking about the creation of the universe. When did it happen? The best model we have is Big Bang theory, which tells us that the universe is 13.8 billion years old. So it all started 13.8 billion years ago. How long did it take to make the universe in which we live? Approximately 3 minutes. And you'll see why that 3 minutes is relevant in due course. So you could argue the universe is still being created. The Big Bang is an ongoing process. But in a very real sense, you could say most of the action took place in the first 3 minutes, and it's all been fairly boring ever since. Where did it happen is a question that often crops up. But if we're talking about the universe, meaning everything, then of course you can't say, well, the universe actually started over there. Basically, the universe started everywhere. So you cannot point to a patch of space, a bit of sky, and say the Big Bang happened over there. It basically happened everywhere because we're talking about the creation of everything. Why did the universe, if it was born 13.8 billion years ago, why did it evolve the way it did? The answer is the laws of physics. Physicists claim everything is because of the laws of physics, because we're a fairly arrogant bunch and we believe that physics explains everything. Why did it evolve the way it did? Because of the laws of physics. How do we know all of this? Same answer, because of the laws of physics. The laws of physics are basically the rules that allow us to understand, or at least to get a handle on, understanding how the universe came to be and how it ended up looking the way it does. I often think about this in terms of a chess game. In other words, we live in a universe and we're trying to figure out what are the laws of physics that tell us about the universe in which we live. Imagine we're not dealing with the universe. Imagine we're dealing with a game of chess. Now, normally with chess, you're told what the rules are and then you go away and play the game. But imagine it was backwards. Imagine you were shown this picture and you had no idea what chess was all about. Can you figure out what the rules of chess are by looking at this picture? And the answer is no. At best, you would say it's some sort of a game. It seems to be played out on a board. There seem to be two sets of colours, a goldy colour and a silvery colour. So maybe it's a game between two people. But you can't figure out what each piece is supposed to do and what the rules are that specify how each piece can move, or even what the purpose of the game is. You can't figure out the rules of the game from a snapshot like that. In much the same way, we can't figure out what the rules of the game are by taking a snapshot of a galaxy. We can't expect to look at an image like that and say, yeah, we can figure out how the universe came to be and how we end up with galaxies that look like that from a snapshot. So, what's the alternative? Well, we can't get the rules of the game from a snapshot of a chess game. What if we could watch a chess game being played? Okay, it might take a few hours, but if we could watch two people playing chess, moving backwards and forwards, watching how each piece moved, then we stand a chance of understanding what the rules of the game are. But we really can't do that with the universe, because we can't simply sit and watch this galaxy to see what it's doing, because it would take a few 100 million years to rotate once, and therefore we just haven't got the patience to sit back and say, let's figure out how the universe works by sitting back and watching it. So we can't take the video analogy and say, let's watch a video of a game being played. What's the alternative? Well, instead of watching a game being played, what we could in principle do is to say, let's not take a snapshot of the game, let's take a snapshot of 1 million games of chess that are all being played at different parts of the world at different stages. Some of those games are in the early stages, some of those games are close to checkmate. If we had 1 million different pictures of lots of games being played, then we would have a chance of figuring out what the rules of the game are, because we could look at enough examples and work out that this piece always seems to stay on this square, so that must mean it can only move in particular ways. And in a sense, it's the same with galaxies. The snapshot of one galaxy doesn't tell us anything. But if we could take a snapshot of thousands, or millions, or billions of galaxies, then we stand a chance of figuring out, even if we can't watch them evolve, if we take enough pictures, we might get a handle on this. Especially when you remember that when telescopes like the Hubble, or indeed the James Webb, take very deep field, we are looking at very faint galaxies that are very distant, and so some of the brighter galaxies might be quite close, and we're looking at them as they were fairly recently, and some of the more distant galaxies are very distant. Light might have taken billions of years to reach us, so we're looking at them as they were billions of years ago. So even though it's a snapshot, we are looking at lots of different galaxies, all at different stages of their evolution, a bit like watching 1 million games of chess being snapshotted rather than watching them progress. But you might say, well, yeah, isn't this all futile? Surely we've got no chance of understanding the rules. This is not the universe. This is just a tiny bit of our immediate neighborhood. It happens to be a little part of Orion, as some of you, I'm sure, will recognize, with the Horsehead Nebula down here and the Orion Nebula off to the top right. The universe, even little bits of the universe, look enormously complex. So surely we'll never really understand the rules that allow these sorts of structures to come into being. Well, bear in mind, just because something looks very complex does not mean it's beyond our comprehension. For instance, if we take an analogy, here's a mathematical collection of colored pixels. It's called the Mandelbrot set. This is actually a tiny part of the Mandelbrot set. In principle, the Mandelbrot set is infinite, and what we're showing here is, I don't know, maybe 1 million pixels or so. And you look at this and you might say, well, isn't it just a set of repeating patterns? Well, no. Some of these patterns look similar to each other, but nothing actually ever repeats. In much the same way that 1 billion stars might be similar to each other, but none of them are identical, or 1 billion people might be similar to each other, but none of them are identical. Similarly, every pixel in the Mandelbrot set, way bigger than just this tiny subset of 1 million, if we were to take 1 billion, or 1 trillion, or quadrillion pixels in the Mandelbrot set, every one of them is unique. And if we zoom in, we see more and more and more detail. And in principle, we can zoom in as far as our computer is capable of calculating what the colors of these pixels are supposed to be. So it's, in a sense, an infinitely complex pattern. So what is the mathematical formula that allows you to calculate each and every pixel of these trillions or quadrillions or septillions or decillions of pixels? The formula that allows you to calculate this, the rules of the game for the Mandelbrot set, is that. That formula allows you to calculate every colored pixel you're looking at and a few trillion in addition. So just because something looks complex does not mean the underlying rules are beyond our imagination or are beyond our ability to comprehend. One of the favorite quotes for me from Einstein was, "The most incomprehensible thing about the world," and in this context, the world, if you like, means the universe, "the most incomprehensible thing about the universe is the fact that it is comprehensible." There's no reason why that should be. We are simply a species of monkey who came out of the trees a million years ago, and we've been wandering around trying to avoid getting eaten. And now we're capable of contemplating the universe and trying to figure out what the rules are. Just because the universe looks complex does not mean it's beyond our ability to comprehend. So what's the flow of thought that allows us to get a handle on what the universe is actually doing? There are a number of different factors here. One is the observation, now approximately 100 years old, since Hubble first gave us this observation. Galaxies are moving away from each other. Spectroscopically, we've been able to measure the stretching of light, the so-called redshift, that tells us galaxies are receding from us. So we've had that observation for 100 years or so. And we conclude, well, it looks like the universe is expanding. And as far as we can tell, it has been expanding ever since it was made. The other piece of information we have, other than looking out, is to look inwards and do experiments here on Earth to try and understand the nature of matter. What are we made of? What is the building made of? What is the Earth made of? What is the sun made of? We can do experiments. For instance, we can do physics experiments like banging things together. We can take fundamental particles and bang them together in the Large Hadron Collider and ask, well, what is the world made of? And what happens if we try and take apart a particle like an atom or a nucleus or a proton or something like that? So experiments here on Earth tell us about the nature of matter, and observations of the universe tell us what the universe is doing on the largest of scales. If we put everything together, we can draw conclusions as long as we make some assumptions. And these are two very important assumptions that we can't prove. We have to assume that the laws of physics in any given place are the same elsewhere. Simply because if they weren't, we would not be able to make any progress whatsoever. If the laws of physics in England were different from the laws of physics in Australia, then nothing we learn here would be applicable anywhere else. And presumably, if it was different in Australia, it would be different in Alpha Centauri and different again in the Andromeda galaxy. We have to assume that the laws of physics are absolute in the sense that what we learn here is applicable beyond our own laboratory, beyond our own planet, and elsewhere into the universe. We also have to assume that the laws of physics now are the same as the laws of physics will be in the future and were in the past. Again, if that's not the case, if we do an experiment and determine what the laws of physics are now, and it turns out it's all different tomorrow, or next week, or next year, then again, we cannot possibly make any progress with our understanding of anything if the rules keep changing. We have to assume the laws of physics are the same everywhere and the same at all times. In other words, the laws of physics are absolutely immutable. They aren't necessarily, but if they aren't, we cannot understand anything. So the only way that we can advance our understanding is to make that assumption, that when we do experiments in the lab, they are equally applicable in the Andromeda galaxy, and they're equally applicable right after the first moments of the Big Bang. If we take the observation that the universe is expanding and our understanding of matter and assume that the laws of physics are the same for both, we come to the conclusion that the universe was created in a hot dense state, a very hot dense state, 13.8 billion years ago, and it has been expanding and cooling ever since. That's a deduction based on observation and our understanding of the laws of physics. And then we come back to the question we're trying to deal with this evening. We know that the observable universe, and again, I'll be talking about the universe, but what I mean is the observable universe, because we've got no idea what's happening outside our ability to observe. Within our observable universe, there's trillions of galaxies, and I don't know how many sextillion stars, and a whole load of gas and dust. Where did all that matter that we see in the observable universe, where did it all come from? We can ask ourselves, how far back in time do we think we can go? If we believe, based on the expansion of the universe now, we can see how fast it's expanding, and we can deduce that, well, it looks like it all started 13.8 billion years ago. How far back in time can we go towards that 13.8 billion years, towards t equals 0, if you like, and still believe that we really do understand what was going on? How far back towards t equals 0 can we go before we give up saying we really don't know what the rules of the game were back then? We really don't know whether the laws of physics we understand today were applicable back at this early period. Can we go back to the first year of the universe's 13.8 billion year history? Yes, we can go back to the first year and we can say, hand on heart, we have got a pretty good idea of what was going on. Can we go back to the first day? Of course, day is a Earth definition of time, but we know what we mean by a day, 86,000 seconds. Can we go back to the first day and say, yep, whatever the conditions were, we think we understand what the universe was like? Yes. What about the first hour? Yes. What about the first minute? Yes. What about the first second? Yes. What about the first millisecond after t equals 0? Do we think we understand what was going on? Yes. What about the first microsecond? Yes. What about the first nanosecond? Yes. What about the first picosecond? No. At this point, we have to say, no, we really don't understand what was going on prior to the first picosecond. 1 picosecond, 10 to the minus 12, 1 trillionth of a second. Prior to that point, it's guesswork. It's speculation, it's conjecture. We're on shaky ground at that point. From this point onwards, from 1 picosecond forwards, right up to the present day, we think we've got a relatively good understanding. It's all relative. We don't say it's perfect. There's still some gaps in our knowledge, but we have a reasonably solid understanding of what the universe was doing, not at t equals 0, but from 1 picosecond onwards. So this talk, that was a rather lengthy introduction to what it is I'm dealing with this evening. So that was the introduction. On the next slide, I'm going to introduce a few basic ideas, some of which you're familiar with and some of which maybe you're not familiar with, because a few basic ideas are what we need before we start on the journey of, let's have a look at what happened when in the very early history of the universe. We'll look at the first fraction of a second, and then we'll look at the first few seconds, and then we'll look at the first few minutes. And it'll take more than a few minutes to cover the first few minutes. We'll then change gear, otherwise we'll be here till Christmas, and we'll change gear and go faster for the next 380,000 years. And again, there's a very good reason why we've chosen that number. And then again, we'll change gear and jump right forward to the present day of 13.8 billion years after t equals 0. So that's what we're going to cover. Firstly, let's cover a few basic ideas that are sort of fundamental to what it is we're talking about. I hope that's no surprise to anybody. We are made of atoms. Atoms are a positively charged nucleus at the center, negatively charged electrons buzzing around them like bees in a beehive. If we wanted to, we could take an atom, positive charge and negative charge, and by various means, it doesn't really matter how, by various means, we could separate those. We could strip the electrons off an atom if we wanted to. And we find that an atom is actually made of a nucleus and electrons. Electrons, we believe, are fundamental particles in the sense that we have no evidence that they are made of anything else. We can't take an electron, cut it in half, have a look inside and say, what is an electron made of? As far as we can tell, we simply cannot do that. So we label it fundamental because it's not made of anything else. Unlike the nucleus of an atom, which is a compound particle, it is made of something else. It's not fundamental. We can, in a sense, cut a nucleus in half and look inside and ask what it's made of. Again, we don't have to worry about how. It is simply possible by physicists generally banging things together in particle accelerators. So a nucleus is actually made of protons and neutrons, as represented by these golf balls. I'll be sticking to protons are red and neutrons are blue. So the nucleus of atoms is some combination of protons and neutrons, neither of which is fundamental because they're also made of something else. When we actually look inside a proton, we find it's made of something else. Let's not worry about why they came up with these stupid names of quarks for the things that they're made of. All that matters is a proton is made of something else. They're labeled quarks, and to the best of our knowledge, quarks are fundamental. We have not found any way of taking a quark, cutting it in half, looking inside and asking what is a quark made of. So we have fundamental particles like electrons, we have fundamental particles like quarks, and they make this sort of Russian doll, if you like, of atoms can be split, nucleus can be split, protons can be split into their component parts. It takes more and more energy as we go down. It's relatively easy to take the electrons off an atom. It's more difficult to split a nucleus into protons and neutrons. It's even more difficult to start looking inside protons. So there's actually an energy scale from low energy to high energy in terms of these structures. But remember, we said on the previous slide that we believe the universe was made in a hot, dense state and has been expanding and cooling ever since. And to a physicist, low energy and high energy are essentially the same thing as low temperature and high temperature. Temperature is really just a measure of how much energy does all the stuff that we're dealing with have. If we're dealing with particles in the universe or gas in this room, for instance, the temperature is just what's the average amount of energy that each molecule or atom or particle has. So if the universe started hot and is cooling down, then there's a time axis, an implicit time axis from the bottom to the bottom to the top, because we're dealing with hot down here and cold up there. That means the universe was made from the bottom up. And we would have to wait until the universe is cold enough before we can start putting quarks together to make a proton. Because if we start trying to put quarks together to make a proton while the universe is still too hot, it'll just shake itself apart. And we have to wait even longer for the universe to cool some more before we start putting protons and neutrons together to make a nucleus of an atom. If we try putting protons and neutrons together before the universe has cooled enough, the universe is so hot, any attempt to bring them together, they'll just separate again, and we can't make a nucleus. Similarly, we have to wait even longer before the universe is colder still, before we can mate up a nucleus with electrons to make an atom, and eventually make atoms into molecules, etc. So that's this sort of ladder, or Russian doll if you prefer, idea that the way that the universe is put together is a sequence as the universe cools that we can go through these various steps to go from fundamental particles to atoms and molecules and eventually us, some rather long time later. So let's start this sequence of time. T equals 0. What happened at the instant of t equals 0, 13.8 billion years ago? Perhaps it's no surprise to say that science cannot provide a definitive answer. Remember, in the very early universe, we're on shaky ground, so we do not know. But a lot of people think that maybe it was a quantum fluctuation. In a different talk, I talk about how weird quantum theory is. We've had quantum theory for 100 years now. Again, like Einstein's general relativity, it's been around since the early 1900s. Quantum theory was put together around about 1930. We've been testing it to destruction since then, and we cannot find anything wrong with it. And quantum theory says it's okay to borrow energy from nothing. You can get something from nothing. It's completely counterintuitive because we don't normally see it in day-to-day life. But quantum theory says, yep, that's perfectly okay. So it's thought that maybe there was a quantum fluctuation in which nothing turned into something. Perfectly allowable, perfectly okay. I know it sounds weird, but quantum mechanics is weird. We just have to live with that. How big can this fluctuation be? Is it going to be big enough to make a universe? Well, there is a limit, according to quantum theory, as to how big a jump you can make. Starting with nothing, how much something can you actually borrow effectively? There's a limit to the product of energy times time. In other words, you can borrow a lot of energy for a short time or a little bit of energy for a long time. So if you say maybe we borrowed energy from nothing to make a universe, well, what matters is how much energy did we have to borrow in order to make the universe? When we look out into the universe, we can make a very rough estimate of how much energy is out there. All of the gravitational energy, by definition, is negative energy. All of the mass energy that's out there is, by definition, positive energy. And when you add it all up, amazingly, it looks like the total might be zero, because all the gravitational energy balances all the mass energy. So perhaps we've actually borrowed effectively nothing at all, or hardly anything at all, which means we don't have to pay back the loan of the energy we've borrowed for a long, long, long time. And I'm sure when you listen to that argument, you say, that sounds ridiculous, which is fair enough, because quantum mechanics is ridiculous. But that doesn't mean it's wrong. But remember, this is still conjecture. This is not theory. This is not part of Big Bang theory. Basically, this is conjecture of what might have happened at t equal 0. Let's move forward from t equals 0. Let's move forward by this many seconds. That's a relatively short amount of time, I think you'll agree. Basically, we're talking about 10 to the minus 35 seconds after t equals 0, the universe has expanded from essentially nothing until it's the size of a golf ball. And a reminder that when I say the universe, I mean everything in the observable universe that we can see. At the moment, the observable universe is a large sphere, approximately 100 billion light years in diameter. And I'm talking about everything inside that sphere used to be a lot closer together. If we wind the clock back far enough, everything inside a sphere that's currently 100 billion light years in diameter used to be separated by centimeters. It is impossible, absolutely impossible, to imagine what we mean by that, because it's difficult enough just to imagine what if we squeezed the Earth down to the size of a golf ball. Even that is beyond our comprehension. But here we're saying that the entire observable universe, if we wind the clock back far enough, used to be inside an object about the size of a golf ball. And just like a golf ball, it had dimples, which is why I like this particular analogy. Not dimples in the sense that it had little depressions in the surface, but it had small variations in this sphere that ultimately would become our observable universe. In this sphere, there were small variations in density or temperature. That's what I mean by dimples. Eventually, when the universe is much, 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 much larger, these dimples, these small variations in temperature and density, would give rise to all of the structure, the large-scale structure in the universe that we see today. Effectively, it'll give rise to clusters of galaxies, superclusters of galaxies, ultimately galaxies themselves. Let's move forward to 1 picosecond, because the last two slides are conjecture. Now we're saying that here we are at 1 picosecond, 1 trillionth of a second after the instant of t equals 0. The observable universe has now expanded until it's about the size of a solar system. Yes, of course, the solar system doesn't exist yet. We're just getting an idea of scale here. So 1 picosecond after t equals 0, the observable universe is now about the size of the solar system, a few light hours in size. So it's gone from nothing to a few light hours in size, but it's only taken a tiny fraction of a second to do that. So clearly the universe was expanding much, much, much faster than the speed of light. I mean, it still is in various parts. When we look out to galaxies in the distant universe, we see galaxies receding from us at greater than the speed of light. Here we're talking about much greater, because it's gone from 0 to light hours in only a picosecond. So its speed of expansion is trillions of times the speed of light. Temperature, it is calculated based on our understanding of how the universe is expanding. The temperature at this point would be about 10 to the power 15 Kelvin. And this is important because we can work out from this temperature what is the energy of any constituents. If we've borrowed energy, we can make matter through E equals mc squared. Whatever matter existed at this early time, at this temperature, we can work out how much energy each of the constituents have. And it turns out to be the same as the energy we can generate in the Large Hadron Collider. So I'm referring to this collection of particles as quark soup. If we borrow energy, we can make anything we like. E equals mc squared means if we've got energy, we can make matter. If we've got matter, we can make energy. We're not just talking about quarks, we're talking about loads of different particles in principle, but just for brevity, I'm just calling it a quark soup because it's made up of lots of quarks and electrons and exotic particles as well, but I don't want to keep listing them, so I'm just calling it a quark soup. So because this quark soup is made up of particles that have energies that we can access in a particle accelerator, that means we can test our ideas. If we think we know what's going on, we can actually test it by banging particles together and seeing how they behave when they have similar energies that were available 1 picosecond after the Big Bang. That's why we say from this point onwards, because we can test our ideas, it's not just conjecture, it's not just hypothesis, it's a theory which is testable because we can actually check by doing experiments here on Earth to see whether we're right or not. That's why we say that after the first picosecond, because it's all testable by experiment, we have evidence that tells us that is the way it was. Matter and antimatter were continually exchanging back and forth. Energy makes matter, but it doesn't just make the matter that we're familiar with, it makes matter and antimatter. Antimatter is a sort of cousin of matter, it's another type of matter, but all of the various characteristics and properties of the matter are different. For instance, if we have an electron that we're familiar with, it has a particular charge, electrons are negatively charged, but there is such a thing as an anti-electron. Every particle has an antimatter equivalent, and if electrons are negatively charged, then an anti-electron is positively charged. These things exist. Positrons, they're called. Perhaps you've heard of positron-electron tomography. In other words, it's a medical technique that allows you to actually verify what's going on inside the human body. So antimatter is not just a theoretical concept. We know antimatter exists. And it is thought that matter and antimatter must be made in equal amounts because that's the only way that seems to make sense when we're talking about energy producing stuff. I don't know how to represent energy in a PowerPoint slide, so I'm just labeling it as E rather than just some nebulous cloud or something like that. If we have energy, and remember we've borrowed this energy originally from nothing, and from now on it's a free ride because we've got this energy, and we can use that energy to make stuff and anti-stuff. We could make electrons and anti-electrons. We could make quarks and anti-quarks. And in the early universe, almost everything was made. Energy made matter and antimatter. Probably not oranges and anti-oranges. Doesn't matter. It made something and its antimatter equivalent. And matter and antimatter will annihilate very quickly after being made and generate energy. And that energy can then be used to make matter and antimatter. Not necessarily the same two objects that it just made. having got the energy back again from the annihilation of matter and antimatter, that energy could then be used to make some other particle and its antiparticle. Probably not a hot dog and an anti-hot dog, but it doesn't matter. It makes something and its antimatter equivalent, which would then annihilate and produce energy again. Back and forth and back and forth. Energy makes matter and antimatter. Matter and antimatter make energy. Back and forth and back and forth. Somehow, and we don't really understand the details of this, matter gained a small excess. We assume that they would be made in equal amounts, literally 50-50. But somehow there was a slight imbalance and more matter was made than antimatter. And I can represent that here by saying we're going to make a whole load of matter and a whole load of antimatter. I've shown the excess here as something like 1 in 10. In other words, implying that there's more matter than antimatter by about 10%. It was nowhere near that big. The imbalance was tiny. The excess of matter over antimatter was not 1 part in 10. It was more like 1 part in a billion. But when we start annihilating matter with antimatter, each of these particles, as illustrated, will annihilate with its antimatter partner, as it were, to produce energy. Generally speaking, energy in the form of light. But the tangerine on the end, whatever particle that is supposed to represent, whether it's a quark or an electron, doesn't matter, it doesn't have an antiparticle to annihilate with because there's this asymmetry. There are different numbers of both. So that matter can't annihilate with antimatter, so we end up in a universe which is full of energy in the form of light, and we have a tiny amount, 1 part in a billion, of matter left over. That 1 part in a billion is everything we see in the observable universe. It's you and me and the Earth and the Sun and the solar system and the Milky Way and Andromeda and all of the trillions of galaxies that we can see are that tiny bit that's left over. If we were to count up how many particles of light, so-called photons of light, are there, we find that there are indeed something like 1 billion photons of light for every particle that's out there. It's a bit difficult to count them all, but we can get an estimate of how many particles are out there when we add them all up, how many photons of light are out there. We find indeed that there are 1 billion times as many photons of light as there are particles. So we are very grateful for the fact that there was a little bit left over, because otherwise we wouldn't be having this talk this evening. Let's jump forward to 1 millisecond after t equals 0. Matter and antimatter are continuing to pop into and out of existence as energy makes the two of them annihilate to make energy. Protons and neutrons are made up of quarks. We can take a proton and tear it to pieces, we find it's made of 3 quarks. We can take a neutron, tear it to pieces, we find it's made of 3 quarks. It doesn't matter about the details as to why I'm labeling these quarks U or D, and why I'm labeling these quarks as either red or green or blue. The details don't matter. What matters is quarks can annihilate with antiquarks to give us energy, which can then make quarks and antiquarks. So in fact, they can swap backwards and forwards and backwards and forwards. A bag of these 3 quarks we call a proton. That's simply the name we give to a bag of 3 quarks that has that particular set of characteristics. And if we have a bag of slightly different quarks, we call that a neutron. So protons and neutrons are just the names we give to this collection of quarks or that collection of quarks. And in the early universe, they could effectively swap backwards and forwards. Protons could change into neutrons, neutrons could change into protons. We are now 1 second after t equals 0. The universe has cooled down a little bit. It's now only a balmy 1 billion Kelvin. It's now too cold for protons and neutrons to change into each other. There isn't enough energy in the universe to allow them to do that. Protons are a little bit lighter than neutrons by about 0.1%. How do we know that? Because regardless of what happened in the early universe, we can measure their properties now. And we believe that protons measured on Earth today are exactly the same as protons in the early universe. There is nothing physically different about them. The same for neutrons. So when we measure protons and neutrons now, and we find that neutrons are a little bit heavier than protons, we have good reason to believe that that must have been the case in the early universe as well. So if protons are a little bit lighter than neutrons, at the point at which they can no longer swap backwards and forwards, we can calculate that the number of protons relative to the number of neutrons is that particular ratio. I've just taken a representative sample of 16 particles. 3/4 will be protons, 1/4 will be neutrons, so that gives us 12 protons for 4 neutrons. You might ask, well, why should you end up with that particular ratio? Well, one argument is nature always favors the lower energy. Or if you prefer, nature always favors the lower mass. One way of thinking of it is to say, if nature is making a whole shed load of protons and neutrons, because these quarks are getting together in the way they are, protons are lighter, so they're easier to make. If they're easier to make, nature will make more of them. And a calculation based on the laws of physics, at 1 billion Kelvin or thereabouts, we would expect nature to make 3/4 protons and 1/4 neutrons. That's after about 1 second. If we go forward a little bit to something like a few hundred seconds, well, we know that neutrons are unstable. How do we know? Because we can measure that in the laboratory now. If neutrons are unstable and some of them turn into protons spontaneously, nothing to do with how much energy is available, it's a spontaneous thing because neutrons are heavier than protons. If it happens now, we have good reason to believe it happened in the early universe. So some neutrons change into protons. So instead of having 12 red and 4 blue, we've now got 14 red and 2 blue, because 2 neutrons, it's calculated, would have changed into protons. So we have a universe that's swimming with a whole load of protons and a whole load of neutrons. By the time we get to 100 seconds or so, the universe is now cooled to 100 million Kelvin. It is now possible for neutrons and protons to get together. Up to this point, the universe was so hot, if you try and get protons and neutrons together, they have so much energy, they just literally separate again. But now the universe is cool enough, I know 100 million doesn't sound cool, but 100 million Kelvin is cool enough for protons and neutrons to get together and start to form structures. Of all the possible structures that can exist, one is much more stable than other combinations. We could indeed get a proton to stick to a neutron, but a much more stable structure is this one. 2 neutrons and 2 protons. That is a very stable structure. And so we get 2 protons marrying up with 2 neutrons, a so-called alpha particle, 2 blues, 2 reds. That is very stable. That is, in a sense, what nature would like to make out of the neutrons. But it can't make an entire universe of this, because once those 2 neutrons have married up with 2 protons, all of these protons haven't got any neutrons to marry up with. You're left with 12 bachelors. And at this point, after 100 seconds, you can't change anything else. After 3 minutes, the amount of protons, which are effectively just the nuclei of hydrogen atoms, and these so-called alpha particles, which can also be regarded as simply the nucleus of a helium atom, the relative amount of hydrogen and helium is fixed. After 3 minutes, it is not going to change. At least it's not going to change until eventually you make some stars which will start fusing hydrogen. But on the timescales we're talking about, after 3 minutes, that's it. All the hydrogen in the universe has been made after 3 minutes. And it's a totally separate story to tell you what happens when all of that hydrogen eventually runs out, because no more hydrogen is being made after 3 minutes. We can now jump forward 380,000 years, and the amount of hydrogen, the amount of helium does not change. Not only that, but we can look out into the universe and say, well, how much hydrogen and helium actually is there? Big Bang Theory predicts there should be 3/4 hydrogen, 1/4 helium, based on the numbers we were previously looking at. When we look at all of the gas in the universe and ask how much hydrogen, how much helium, it turns out what's out there is 3/4 hydrogen, 1/4 helium. Big Bang Theory predicts the ratio of those two gases, and it gets it right. Nothing of any interest whatsoever happens for the next 1/3 of a million years or so. The universe continues to expand, the universe continues to cool. The hydrogen is still there, the helium is still there, it's just getting cooler and cooler, and all of the various protons, neutrons, etc., they're all just drifting further apart. Eventually, the universe cools to a particular point, 3000 Kelvin. Why is 3000 Kelvin a particular point of note? It takes this many years for it to cool to 3000 Kelvin. But 3000 Kelvin is relevant because it is the temperature at which a nucleus can hang on to its electrons. Prior to this, the universe was so hot, if you take a nucleus of helium or a nucleus of hydrogen and try and get an electron to stick to it and orbit around it, well, the universe has too much energy and it would just strip the electron straight off. But now, after 380,000 years, the universe is cool enough for a proton to hang on to an electron and make an atom of hydrogen, or indeed helium nucleus, hang on to electrons and make helium atoms. So for the first time, the universe changes from a mess of positive and negative charge. Now the negative charge is locked up in atoms. For the first time, atoms exist. After 380,000 years, this is the first point at which the universe contains atoms. And as soon as you have atoms, which are electrically neutral, because you've got a positive nucleus and a negative electron, in total, no net electric charge, the universe at this point becomes transparent. Up to this point, the universe was a plasma. Light couldn't get through this plasma. Like a pinball machine going through a pinball machine, it was rattling off all the positive and negative charge, and it couldn't make any progress. But when the universe turns transparent, the light is released and can fly across the universe. So light up to this point was trapped in the plasma, but now the light can fly across the universe. And we can see that light today. If you like, it's the afterglow, or sometimes called the echo, of the Big Bang. How hot was the universe? 3000 Kelvin. 3000 Kelvin is white hot. Huge amounts of visible light and ultraviolet light were released. So where do we see this light today? Well, the universe is now much bigger than it was 380,000 years after the Big Bang. The universe is approximately 1,000 times bigger than this particular point in time. If the universe is 1,000 times bigger, light that was released, visible light that was released at this point, has been stretched 1,000-fold. The wavelength of visible light is about a micron or so. Stretch that 1,000-fold, you end up with electromagnetic radiation that isn't a micron wavelength, but is millimeter wavelength. It's microwaves. So the afterglow of the Big Bang is the microwave background. When we look out into the sky, this is an all-sky map that's been wrapped up into this egg shape. When we look out into the sky, we see microwaves coming from all directions. And this is another prediction of Big Bang Theory. It says there ought to be microwaves visible in all directions at this particular energy level, at these particular wavelengths. And that is precisely what was found in the 1960s. It's essentially coming from all directions, but there are little variations. There are some regions that are a little bit higher intensity and some regions that are a little bit lower intensity. It's not as dramatic as this color chart would indicate. The differences between the high intensity and the low intensity parts of the microwave sky are only fractions of 1 part in 1,000. It's essentially the same in all directions, but there are fluctuations. What are those fluctuations? Well, they basically are the dimples in the golf ball that we saw before. variations in temperature in the very early universe have been imprinted on the cosmic microwave background. So those small variations that we see in the all-sky map are effectively a map of the dimples in the golf ball. That's why there is so much interest in the cosmic microwave background, the CMB. That's why various space telescopes have been built, as well as various ground-based experiments have been done to look at the cosmic microwave background, because if we study those small variations we can see in the background, it's telling us about the very, very early universe. We can get a feel, or at least some sort of a feel, for what's actually going on. We can't do a simulation of the entire universe, but we can ask, if we have variations in density and temperature in the very early universe, can we see what happens as the universe evolves for billions of years? We believe that these dimples in the golf ball ultimately give rise to the large-scale structure of the universe. And we have some reason for believing that, because we can run simulations that say, let's start not with a tiny, well, not take a golf ball. We're not going to take the entire universe, the entire observable universe. We're just going to take a large chunk of it, fill it with matter, and produce small variations. This blue color, the shade of blue, tells us about either the temperature or the density of material. Perhaps you can see it's slightly mottled, because although we're taking a large chunk of the universe and filling it with matter, we're putting in small variations of density, small variations of temperature. And now we're going to run the simulation and say, let gravity do its stuff and see what happens for the next few billion years. If we do that, the blue colors will change. The brighter colors indicate denser regions. So let's see what happens when gravity takes effect. Dense regions become even denser, and some regions become less dense. And clearly, some regions are getting very dense. This is where galaxies and clusters of galaxies, etc., are being born. Gravity takes the original relatively smooth uniform distribution of matter and concentrates it to give us the sort of structure that we see in the universe. Remember the very first animation that I showed, this fly-through of a 3D. The galaxies are not uniformly spread throughout the universe. They are often in lines or filaments, and they seem to often lie on this web-like structure. And simulations show us why, because the simulations are saying, let's start with a chunk of matter, let's apply small variations that we think were there because of the original variations in the golf ball, as we can see in the cosmic microwave background. Let gravity do its stuff for a few billion years. Hey presto, we end up with galaxies and clusters of galaxies and superclusters of galaxies. So that's not proof, but it gives us strong evidence that the Big Bang is the right sort of theory, because it's A, predicting the right amount of hydrogen, it's predicting the cosmic microwave background, and from that early universe we can get a universe that looks very similar to the universe in which we live today. If we were to map out our immediate neighborhood, there's the Milky Way galaxy, surrounded by lots of rather small satellite galaxies. This is the local group. We've got the Andromeda galaxy down there, for instance. But we can't see the large-scale structure of the universe by only looking at our immediate neighborhood. If we come outer scale, so that the local group is now in this region, we can see that there are other clusters around us. We have the Virgo cluster over there. We have a Fornax cluster down there. We have an Eridanus cluster down there. You can already start to see that these clusters aren't randomly scattered over three-dimensional space. These clusters seem to form a little bit of a line from bottom left to top right. There is a filament here that's made up of cluster after cluster after cluster, or supercluster after supercluster. If we zoom out even further, we see that there's the local part of our universe here, the Virgo supercluster, and we can see all sorts of other superclusters all over the place. But again, it is not uniform. It is quite definitely mottled, in which we have some regions which are very highly populated with galaxies, and there are some regions where there appear to be almost no galaxies at all. This Capricornus void, for instance, or the Boötes void. The fact that we have a mottled structure with lots of galaxies here and no galaxies over there, that's a reflection of the fact that the original golf ball had dimples in it. It's very difficult to map them one-to-one, but we are fairly convinced that the variations that we see in the cosmic microwave background, which are produced by the dimples in the golf ball, they have formed the large-scale structures of the universe that we see around us. What happens for the next 13.8 billion years? Well, remember, in principle, it only took 3 minutes to make all the hydrogen. If we live in a universe that's full of hydrogen, we know how stars work, so we know that we've got lots of galaxies and those galaxies are made of stars, and we know the stars are eventually going to turn the hydrogen into the heavier elements such as us, the carbon, nitrogen, oxygen, phosphorus, calcium, everything that we need for us to be us. So we know how galaxies and stars work as long as we start with hydrogen, and as I say, we only need 3 minutes to make all the hydrogen, so that's fine. Once we've got hydrogen, we understand galaxies, and we understand stars, and of course we then understand planets, and we understand trees and mountains and snowflakes and rainbows and cats and essentially everything. Okay, we don't understand cats. Yeah, okay, we don't understand cats. So there are still some details of cosmic evolution to be worked out, for sure. I'm obviously glossing over a great deal of facts here. But the bottom line is, if you start with enough hydrogen and wait long enough and let gravity do its stuff, then essentially everything else flows from that. So let me just remind you with a ridiculous timeline what it is I've been talking about. We've been talking about the observable universe that's currently 100 billion light years in diameter. Speculation is that it used to be only the size of a golf ball. This is conjecture. And then it expanded up to about a picosecond. We had a soup of fundamental particles. It's called a quark soup in this talk, but it's really a soup of lots of quarks, lots of electrons, lots of exotic particles. Doesn't really matter what. Energy was borrowed from nothing to make all of these particles. After a fraction of a second, we can start to put some of these together. We can gather the quarks together, and in a particular combination of quarks we call protons, or another combination of quarks we call neutrons. Once we've got protons and neutrons, a little while later, after about 3 minutes or so, those protons and neutrons can get together to form one of the most stable structures, this one called an alpha particle, otherwise known as the nucleus of a helium atom. And then the bachelors that are left are basically the nuclei of hydrogen. If we were to wait 380,000 years, the universe will have cooled off enough that electrons can then be caught by these positively charged nuclei. The electrons, remember, were in this soup along with all of the quarks. After 380,000 years, atoms form, the universe turns transparent, light is released, and we see that light stretched 1,000-fold as the cosmic microwave background. We're not absolutely sure what happens next, or at least we're not sure of the timescale of what happens next. Once we have the cosmic microwave background, because the universe has turned transparent, we have all the raw materials we need to make stars and galaxies. But we're not dead sure how long that takes. There was a period after the cosmic microwave background was released called the Dark Ages. How many millions of years, how many hundreds of millions of years did it take between the cosmic microwave background, which is a point that we know in terms of timing, how long until the first stars were actually made, which then formed the first galaxies? That's one of the reasons the James Webb Space Telescope is up there, looking back in time as far as possible. It's looking back to the first 500 million years, back to the first 400 million, back to the first 300 million years, trying to see when did the first stars actually switch on. In other words, how long were these dark ages before we have stars being born and galaxies being born? And of course, we can see galaxies close to us, and we can see galaxies at some distance. James Webb is simply trying to push that as far back as possible to see how far back we can go before we can say that's when the first stars started, that's when the dark ages finished, effectively. So yes, I have to admit that I've skirted over some details when I'm talking about the beginning of everything. The jigsaw is not complete. There are still some fairly serious questions that we haven't yet addressed. Why did matter win? We are fairly convinced that matter and antimatter originally were made in equal quantities, but somehow they got out of balance. Just as well because we are the result of that imbalance, that asymmetry. The excess of matter over antimatter, 1 part in a billion, is responsible for all the matter we can see in the universe. What caused that asymmetry in the first place? We're very grateful it happened, but we'd still like to understand why it happened. And I've been talking about all the matter we can see. What about the matter we can't see? We think there's dark matter out there that causes the galaxies to rotate at speeds which don't seem to agree with the number of stars and the amount of gas and the amount of stuff that we can see in galaxies. The same is true for galaxies in clusters as well. And something is not only allowing the universe to expand, it's also accelerating the expansion. We're calling that stuff dark energy. We're giving it a name, but we really don't understand what it is. Something is causing the universe expansion to accelerate. Even though you would expect gravity to be putting the brakes on and the expansion of the universe ought to be slowing down, we found about 20 to 30 years ago, actually, there's evidence that the expansion is not slowing down, it's actually accelerating. There's even more recent evidence that maybe the actual acceleration itself is changing. We simply don't know. I titled this talk The Beginning of Everything, but I've been trying to be very careful to make it clear that I've been talking in the context of the beginning of everything that we can see. Everything in terms of all the galaxies, all the stars, all the gas, all the dust. Where did all that come from? And I've given you that story. But all of the stuff that we're describing, the galaxies, the stars, the gas, the dust, everything that we can see is only 5% of everything in the universe. The other 95% is this mysterious dark energy and dark matter. And that is still very much a mystery. But that's another story. Thank you all very much.